Okay, so the limits and continued examples. One, sketch the function f of x is equal to x squared minus 4 over x minus 2 when x is not 2 and 4 when x is equal to 2. Determine whether f of x is continuous at x is equal to 2. So I brought back these questions deliberately. None of you managed to find the correct solution in the task I gave. So, solution, as you can see that the function on top there, the x squared minus 4 over x minus 2 is not defined when x is 2, but we've been taught that when x is 2, the function is going to be 4. So you plot the 4 as a point, 2, 4, and then anything else, you use that function. But we're able to simplify this function to x minus 2 and x plus 2 over x minus 2, giving us x plus 2. So now we'll sketch the line x plus 2. So what happens when, so now we have f of x is equal to x plus 2, but remember, not for x is equal to 2. This is only for other numbers. So let's see what happens when x is 0. We'll have 0 plus 2, which is 2, meaning that we have gotten the y-intercept, 2, and then we get x plus 2 equated to 0. We'll get x is negative 2. So I've gotten the x-intercept, and then we're able to sketch this function. Like that, like this. So we're supposed to open up here and leave the hole at 2, 4 as we sketch this function. But because of this piece down here, you notice that that thing there has been closed even before the line came. So it could not show that there's something there. So we have done the sketch. Now we must determine if it's continuous. To determine continuity, 1, you check if it's defined at 2. So f of 2, as you can see from the definition, it's 4. 2, we must check if the limit as x goes to 2 of f of x exists. Now for the limit sake, we're going to use x plus 2, the redefined one, and we'll get 2 plus 2, which is 4. And then part 3, you're comparing if the answers we got in 2 we got 4, which is the same thing that we got in part 1. Hence, f of x is continuous at x is equal to 2.
Sir, I'm sorry, but I'm kindly asking if you can just repeat this part here, this part while you are writing these solutions here. That's just this last part here.
The part about these steps here.
I don't know where, but this part, this side where the Roman numerals, just how you're getting the limits and everything. Just
Okay.
here how you are, yes.
All right. So it starts from here. How do you check if a function is continuous? One, you check that. How do you check the continuity at x is equal to c? You check that f of c is defined. After that, you get the limit as x goes to c of the function f. Does it exist? If it does exist, then you compare in the last step, you compare if the limit you got is the same as the value of the function at that c. If these three are satisfied, then the function is continuous. Now, in our case here, we get the value c, which is 2. What is f of 2? The function says it is 4 when x is 2. So f of 2 is 4. Next thing, the limit as x goes to 2 of x plus 2 is equal to, so why have we gotten x plus 2? Because that's the function that we're having. X squared minus 4 over x minus 2, which we have simplified to x plus 2. So we'll get, you substitute where there's x, you take 2. So you have 2 plus 2, which is 4 as our limit. Then in the third step, you compare now the limit value that you have gotten in part 2 and the function value that we've gotten in part 1. If they are the same, then we say the function is continuous.
Okay, I think I get. Thank you.
Yeah, you think that's a good thinking. Another example. Another example. Example 2. Sketch f of x is equal to 2 plus x for x less or equal to -1. X squared for -1 less than x less than 1. And 1 plus x, is it 1 plus x? 1 minus x for x greater or equal to 1. Sketch, then determine if f is continuous at x is equal to 1 and at x is equal to -1. Let's determine that continuity after sketching. Now pay attention here. This is what you failed to sketch. When you were trying, you were sketching anyhow. Your graph would reach anywhere. So how do you graph this? This function here is the same as separating it where you say, I have f, it's a function 2 plus x. only when x is less or equal to -1. I have f is a function x squared only when x is between -1 and 1. I have f is a function 1 minus x only when x is greater or equal to 1. Only in those cases. So we start. We sketch the first function, this one here. So we have the graph put here. This function has values of x that are less or equal to -1. So we'll start from -1. What is f of -1? F of -1 in that function is 2 minus 1, which is 1. So we get 1. And put a closed point here because the point is included. It remains 2 plus x for the number that are less than -1. For example, at our own choice, we get 2, -2. So we have 2 plus -2 giving us 0. So we have another point, -2, 0. Then we can sketch. This is the function. So we have sketched this function here. Then, if the values of x are from -1 to 1, you no longer use 2 plus x. You now use x squared from -1 to 1. You use x squared. So we are saying, since -1 and 1 are the boundaries, you need to use them. You get -1 squared, which is 1. So this one is supposed to be open here, but because -1 with the top function closed, we'll just start from there and not do anything to it. We can't open what another function has closed. Then we also have 0 to be part of this interval. Since 0 is bigger than -1 and less than 1, we use it. 0 squared will give us 0. So we have a point here. And then 1 squared is equal to 1. So we have an open point there because 1 is not included and no other value has closed that point. So now we'll sketch in this way. Then from there, we go to f of x is 1 minus x when x is greater or equal to 1. F of 1, where 1 is now included, is 1 minus 1, which is 0. So that's 0, we include it. We are free to use any other number bigger than 1. Let's say 2, so you have 1 minus 2 is -1. So if we had 2 here, we're getting -1 somewhere here. So we draw in this direction. So this is the graph of this function. And we are done sketching. Is it okay how the sketch is coming about?
Sir, this the last point we did where we've used 2. Can you just redo that again?
So when you use 2, you're using 2 in this one here, because that's where 2 is found. 2 is bigger than 1. So when you're calculating, you say, okay, then f of 2 is going to be in this very function where there is x, we put 2. So we'll get -1. And then plot it as a point.
So, sir, for this one, meaning for the last one that Chanda just asked about, it's the same as the first one, where since it's just given us, it hasn't given us a range, it's just given us, so we just pick any numbers. Like for the first one, as long as it's less than -1. There.
Exactly.
Okay. And then, sir, I get my intervals, yes, but then this part, okay, please just give me the shortest way to know how I'll know that this one is closed and open, because I don't know.
That's the very easiest short thing. Greater or equal to closed. Less or equal to closed. Greater, open. Less, open.
Okay, thank you very much. That's very helpful.
Yeah. Okay. Now we determine if the function is continuous at x is equal to 1. Okay. At x is equal to 1, is a function continuous? For a function to be continuous, we must check that 1, f of 1 is defined. So what is f of 1? We go where 1 is included, the greater or equal to or less or equal to 1, which is this last piece here. So we have 1 minus 1 giving us 0. So the value of f of 1 is 0, and 0 is defined. So since 0 is defined, f of 0 is defined, we move on. We go to the second piece and look for the limit as x goes to 1. Now look at the function. We have two pieces of the function that are surrounding 1 from right and from left. This means that we need to check for the right direction and the left direction. So as we get to 1 from right, we are going to be using this function here. It's a function which goes to 1 from right. Okay? And this function here is given in the question by 1 minus x. So in getting the limit, we'll put 1 minus x here and substitute, we get 0. This is not the only limit as we approach 1. We also have 1 approached from left, where now we don't find 1 minus x, but we find x squared. So 1 squared is equal to 1. Now, because the two side limits as we approach 1 are different, then the limit as x approaches 1 of f of x is, we say is not, we say does not exist. Does not exist. This is because the left and right limits are different. So we cannot choose any if they are different, represent the limit without a direction. Now, if the second step is not satisfied, we can't go to the third step. The only thing we do is we say hence f is not continuous at x is equal to 1. We also check at x is equal to negative 1. 1, what is f of negative 1? We look for where negative 1 is defined, is included, which is the first piece there. That's why I find less or equal to negative 1. So we have 2 plus negative 1 giving us 1. 2, we check for the limit as x approaches negative 1 from right. Which piece of the function goes to negative 1 from right? If you look at the graph, you'll notice that we are going to negative 1 from right using this curve here. And this curve is x squared. So we have x squared here. So we get negative 1 squared, which is equal to 1. We also check for the limit as x goes to negative 1 from left. Now from left, if you're coming from left, going to negative 1, the only function that you'll be meeting is this function here. And this function here is for 2 plus x. Okay, it's a line of 2 plus x, so we use it, 2 plus x, giving us 2 plus negative 1, which is equal to 1. So we have the limit as x goes to 1, as x goes to negative 1. Since the two side limits are equal, then the limit in general is equal to 1. And so it exists because it is known. Then the third step, we compare now. Since the limit exists as we approach negative 1, and it is 1, is it the same as f of 1? They are the same. We got 1, even the limit is 1. What does this mean? This means that f is continuous at x is equal to negative 1. Do we have questions?
So I've got a question.
Yes.
Since here in this question we've been given, we're being asked if x equals to 1 or x equals to negative 1 is continuous. So does that mean, like, since here we've got two different plottings, so you can't connect them, like here where we have it's open here at 1 comma 1, and then here where it's closed at 0 comma 1. So here we can't connect it.
We can't connect these two lines. It's very, very hard for us to do. Another question. So as we agreed that I'm going to give you an assessment this one thing. Today is 14th. So I'll give you by somewhere 28. So I was checking the calendar here. The calendar is where it's here. 28 will be Tuesday. 27 will be Monday. I'll give you on 27 on Monday, so that there is no excuse of quiz from the school. Hey, but we agreed, Janet. And I said it's going to be called exam 1 from topic 1 up to calculus. In fact, the whole course. Choose 5 out of 7 questions written in 3 hours. It's on that you are home, or I'll have to invigilate you physically. Because I'm worried I may receive excuses. I don't need to be during the day when there will be power. Even if there's no power, there's no darkness. The whole course. Okay. So I'm doing that so that we can find a good way of revising. Because where we are now, we need to be moving with everything from topic 1 up to calculus as we add on new things. These first topics must be at our fingertips here. So I spend much of my time trying to predict what Mr. Ankuku may bring. If I don't manage to predict the numbers, I'll predict the concepts. It will be as nice as his exam. Okay, so
it won't be nice.
eh?
That means it won't be nice if you say to be as nice as his exam.
As far as the exam preparation is concerned, it will be nice, but a bit hard. You must be ready for a 30. Okay, let's log out and get back. The last 15 minutes, you can do something. But I also give you another question so that you can see if you are now able to sketch this. So do one more sketch and some open limit questions.